This is the video for our paper. Find what you want. Learning Demand Conditioned Object Attribute Space for Demand-Driven Navigation. The task of visual object navigation involves an agent's ability to locate a particular object within a given scene. To successfully accomplish the visual object navigation task, two essential conditions must be fulfilled. First, the user must know the name of the desired object. Second, the user-specified object must actually be present within the scene. However, in real-world scenarios, it is often challenging to ensure that these conditions are always met. For example, humans in an unfamiliar environment may not know which objects are present in the scene, or they may mistakenly specify an object that is not actually present. Nevertheless, despite these challenges, humans may still have a demand for an object, which could potentially be fulfilled by other objects present within the scene in an equivalent manner. Therefore, it is crucial for agents to learn how to comprehend and interpret human demands. Hence, this paper proposes demand-driven navigation, which leverages the user's demand as the task instruction and prompts the agent to find an object which matches the specified demand. The demand-driven navigation has several benefits. First, users no longer need to consider the objects in the environment, but only their own demands. Second, the mapping between demands and objects is many-to-many. In other words, a demand instruction can be satisfied by multiple objects, and an object can potentially satisfy multiple demand instructions, which can theoretically increase the probability of an agent satisfying user demands in comparison to visual object navigation. Third, the demands, when described in natural language, have a wider descriptive space than just specifying an object, and the tasks are thus described more naturally and in accordance with the daily habits of humans. The demand-driven navigation task presents new challenges for embodied agents. First, different real-world environments contain different objects, and, even within a fixed environment, the categories of objects can change over time due to human interaction with the environment. Second, the many-to-many mapping between instructions and objects requires agents to identify what objects potentially exist in the scene to satisfy the user's demand, and where these objects are most likely to be located. Third, the agent needs to determine whether the current objects within the field of view satisfy the user's demand from the object's visual geometry. It is important to note that if an object can fulfill a demand, it is because one of its functions or attributes can satisfy that demand. In other words, if multiple objects can fulfill the same demand, the objects should have similar attributes. Given that the relationship between attributes and demand instructions is common sense knowledge, many mappings between demand instructions and objects are established with GPT-3. The demand instructions are encoded by a BERT model, and the object names are encoded by a CLIP text encoder. We concatenate the demand BERT features and CLIP textual features, feed them into an attribute module, and train the attribute module using contrastive learning. The positive and negative sample definition depends on the satisfying relationships. If two objects can satisfy the same demand, then the two demand object features corresponding to these two objects and the demand are positive sample pairs, otherwise, they are negative sample pairs. During navigation, we load the attribute module trained previous. We first use DETR to crop object instance patches in the ERGB input. Then these patches are encoded by a CLIP visual encoder, concatenated with the demand BERT features, and fed into the attribute module to obtain the aligned demand conditioned attribute feature. Finally, we use imitation learning to train the policy. Here are the results of the quantitative experiments demonstrating the superiority of our method. This is a visualization of the trajectory of our experiment. In conclusion, this paper proposes demand-driven navigation, which requires an agent to locate an object within the current environment to satisfy a user's demand. The existing visual object navigation methods are modified to fit to the proposed demand-driven navigation task, and they have not been found to have satisfactory performance on the demand-driven navigation task. This paper proposes to learn demand conditioned object attribute features from LMs and align them to visual navigation via CLIP. Experimental results on AI2 Thor with the ProcThor dataset demonstrate that the proposed method is effective and outperforms the baselines. Thank you for watching.